All right, welcome back, everybody. So we have section 3.1 finishing off section 3.1 today. Just to give you guys a heads up, we're doing 3.1. 3.2 is only a one-day lesson. We'll do that tomorrow. We'll do a workday on section 3.2 on Thursday, and then we're jumping to section 3.3 on Friday. Just so you guys are aware, we are going to have another quiz next Wednesday, the 3rd of November. Okay. Whose birthday? Oh, yeah? Welcome back. Yep. All right. So let's talk about where we were at on Thursday. Remember, all of chapter 3 is the chapter where we, get to learn all the shortcuts to all the difficult stuff we did in chapter 2, where we were finding the derivatives using the long way around, right? Using the f of x plus h minus f of x all over h and the limit going to 0, right? As h goes to 0. Now we're going to learn shortcuts to that. And we started off with finding the derivative of a constant. Remember, the derivative of a constant is always 0, right? The derivative of a constant is always 0 because if I have the graph of a constant, horizontal line, slope's always going to be 0. And then we started talking about, well, what's the derivative of just x? The derivative of just x is always 1, right? Because if you examine the slope of y equals x, it's always going to be a positive 1. And then we started going on and on and on and seeing, okay, now we see we have this thing called the power rule. And I believe it was right there. The general power rule, where we learned that any polynomial function, and I should, generalize that yet, that any power you could find the derivative of by bringing out in front, reducing the exponent by a factor of 1, and multiplying to that previous exponent. Right? So if you've got like a 3x squared, or actually just say, let's say x to the third. You got an x to the third, you bring that around front, make it a 3x squared. And that not only applies to whole numbers, but also fraction powers and negative exponents as well. If n is any real number, that process still applies. Okay? So here we are. This is new. This is the new part here. We have this thing called the sum and difference rule. The sum rule and the difference rule. And actually, you know what? Let me pull it onto the next page for us, because I can show you both the sum rule and the difference rule at the same time. Here's the sum rule as well as the difference rule. Yeah. The sum rule as well as the difference rule. It basically says that if you have two differentiable functions, two functions where you can find the derivative, you can find the derivative of them separately and add them back together. So if you have f of x plus g of x, and you wanted to find the derivative of f of x plus g of x, it is truly equivalent to basically like the distributive property of that thing. The derivative of f of x plus the derivative of g of x. And the same thing applies to not only sums, but differences as well. The negative doesn't really affect anything. As long as f and g are both differentiable, then you can find the derivative of the sum by finding the derivative of the parts of the sum. Same thing with difference. Okay. Now, using your constant multiple rule as well, where we had like c times f of x, and you could take that as like the derivative of f of x and then multiply c back onto it. So if it's like 7 times f of x, you can find the derivative of f of x and then remultiply it back to 7. Using that, combined with these two rules, you can find the derivative of any polynomial function you would like. And that is an extremely useful thing to do. Okay, can I show you? Anybody sending this? 1 second. Okay. This, I'll tell you what, folks. If I had to use the definition of a derivative that f of x plus h minus f of x all over h on this next problem, oh my gosh, it would probably take me like the entire period to do. Okay, but because we know these rules now, I can find the derivative to this in like 2 seconds. Appreciate what we're going to do here. Think about if you had to use the definition of the derivative. F of x plus h minus f of x all over h. Finding x plus h to the 8th power. Holy chicken nuggets. That would be brutal in and of itself. Okay, so appreciate what we're going to do here. Do you see how there's a bunch of terms? And I'm finding the derivative of this entire function. Basically, I can find the derivative of each piece of that function by itself. So, what's the derivative of x to the 8th? What's the derivative of x to the 8th? 8x to the 7th. To the 7th, right? Almost said to the second. 8x to the 7th. Okay, what's the derivative of 12x to the 5th? Bring the 5 in front and multiply. 12 times 5 is 60. 60 x to the 4th. Okay? Bring the 4 in front, multiply. Minus 16 x to the 3rd. Plus 30 x squared minus 6. What happens to my constant? It would go to 0. The derivative of a constant is always 0. Please don't confuse me saying that the derivative of a constant is 0. Don't confuse that with the limit of a constant. Remember, I kept saying the limit of a constant is the constant. Be careful. The derivative of a constant is not the constant. The derivative of a constant is 0. Okay? Watch out there. The derivative of a constant is 0, meaning it will go away. Okay? Man, appreciate the rule here. We just did this problem in like a minute, where it would have taken us literally the entire period to work out the problem using f of x plus h minus f of x all over h. Oof, that would be rough. Okay. So now let's expand on that. Find the points on the curve of x to the 4th minus 6x squared plus 4, where the tangent line is horizontal. Ooh, that's kind of interesting. Where the tangent line is horizontal. Now, let me think about something. No matter what the function looks like, weird, right? Where are the tangent lines horizontal? Where are the tangent lines horizontal of this function? Think about the tangent line. Okay, it's here. That's vertical. Ooh, right there, right? So the tangent line is horizontal here. Anywhere else? Right there as well. Right there as well. So where did I draw? Like, where were all of those tangent lines horizontal? At all of the maximums or minimums, all the peaks or valleys, right? So what we're doing here is we're identifying where are those peaks and valleys. Now, how do we do that? Well, what's the slope at each one of these points? What's the slope? 0, right? Because isn't a horizontal line slope 0? So the slope at each one of these points is 0. So what I'm going to look for, I want to look for when the slope is 0. That's truly what I'm looking to find. Okay, well, what kind of equation is the slope? The derivative is the slope, right? The derivative is the slope. So let's find the derivative. Let's find y prime. Because the y prime is the equation of the slope. Oh man, this is so easy with our polynomial rule. 4x to the 3rd minus 12x. And the plus 4 goes bye-bye. Because it's just the constant sitting out in the end. So that's the equation of our slope. Well, I want to know when the slope is 0. 4x to the third minus 12x equals 0 is going to tell me where my tangent line is horizontal. Factor out the 4x, leaving an x squared minus, what would that be, 3? So we can set 4x equals 0 and x squared minus 3 equals 0. So x equals 0 when I divide the 4 over, and then x squared is equal to positive 3, so x is equal to plus or minus radical 3. So this function has peaks or valleys at those 3 spots. Yes, I said 3, and I said that correctly. Those 3 spots. At negative radical 3, at 0, at positive radical 3. Let's look at it on a graph just to verify that. Let me see what it looks like real quick. Okay, let's go y equals, get out of here. Let's go y equals, it was x to the 4th, minus 6x squared plus 4. I'm going to zoom 6, but I think I'm going to have to like zoom fit this as well. Oh, no, I don't. Look at the peaks and valleys. Do you see the peak at 0? Okay, that was one of my zeros of my derivative, wasn't it? Do you see positive radical 3? Remember, radical 3 is just like 1 point something, close to 2. Right? The square root of 4 would be 2. So 1 point something, negative 1 point something, right? So what am I saying here? The points where the derivative is equal to 0 actually get us our peaks and valleys, which is something we're going to use a ton once we get into chapter 4. All right, let's take a look here. The equation of motion of particles is s equals 2t to the third minus 5t squared plus 3t plus 4, where s is measured in centimeters and t in seconds. Find the acceleration. Acceleration as a function of time. What is the acceleration after 2 seconds? Now, if I'm thinking about position, and s is position, right? S is position here. It is not velocity, it is position. If I'm thinking about position, S is equal to 2t to the third minus 5t squared plus 3t plus 4. What is the derivative of position? Does anybody remember? What's the derivative of position? It's velocity. Derivative of position is velocity. So if I want to find S prime is really equivalent to V. S prime is truly equivalent to V. The derivative of position is always velocity. Okay. Well, let's figure out velocity. I guess I should stop there for a second and figure out velocity. 2 times 3, 6t squared minus 10t plus 3. What happened to my plus 4? It went bye-bye because it was just a constant. Okay. Well, what is the derivative of velocity? Acceleration. The derivative of position is velocity. The derivative of velocity is acceleration. Okay, well, let's just do that process again. 12t minus 10. So what did we really calculate in terms of position? Double derivative. And what is the acceleration after 2 seconds? Well, okay, let's find a of 2. 12 times 2 minus 10. So 24 minus 10, so 14. Centimeters per second. Squared, right? Centimeters per second. Acceleration is always units per second squared, right? Yeah. 14 centimeters per second squared. So it said find the acceleration as a function of time. Okay. And then what is the acceleration after 2 seconds? 14 centimeters per second squared. I have to tell you guys, that would have taken us like a very long time, like 20 minutes to do that problem, if we were forced to use the definition of a derivative. But because we know this rule where we bring it out front and we multiply and blah, 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 man, that simplifies our life greatly. Okay? All right. I just blah, 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 a lot of stuff there. Yeah. All right, exponential function. So we talked about polynomials. Let's talk about exponentials. What is the difference? What is the derivative of exponentials now? Now, if we try to compute the derivative of the exponential using the definition of a derivative, using that f of x plus h minus f of x all over h, watch what happens. And this is the function that I'm working it on, b to the x, where b is just any number, any constant, right? Like 3 to the x, or 4 to the x, or 2 to the x, or e to the x if we would like it to. Just a number to the x, and we're just generically calling it b. All right, so this would turn into b to the x plus h minus b of x all over h, right? Okay, let's do some manipulation with that. Remember that b to the x plus h, what causes addition up in an exponent? Multiplication down below, right? So b to the x plus h is really like b to the x times b to the h, right? Just breaking it apart a little bit. And then notice here that I've got 2b to the x's. Okay, let's remove it. b to the x times b to the h minus 1 all over h. Now, what's cool about this is that b to the x, what happens if I plug in h is 0 to b to the x? Nothing, because it doesn't depend on h, right? If I plug in h equals 0 into b to the x, nothing happens. So what we can do is actually remove it out front. That's a technique that we'll use a little bit later on. When something is not dependent upon the value that you're taking the limit to, like I don't have a variable h within that term, you can actually bring it all the way in front of that limit and not even worry about it till later. So b to the x times the limit of h goes to 0, b to the h minus 1 over h. Now, notice that the limit is the value of the derivative of f at 0. Okay? If I plug in 0 as a function, as like my variable here, my x, what is b to the 0 power? 1. Rang right as I did that. B to the 0 is 1. So the function, the value of the derivative, when I plug in x equals 0, ends up canceling this term and ends up with just this piece here. So that's really interesting. I just said the value of the derivative at 0. We just calculated that, right? Did we calculate the value of the derivative coming out to be 0? So f prime of 0 is going to be equal to that thing. So what's interesting to point out is that I can take f prime of x is actually equal to f prime of 0 times b to the x. This is actually going to give us a little bit later on, it's going to give us our rule for exponentials. F prime of 0 times b to the x. Okay, we'll use it for natural logs as well. Okay. This is going to be the extremely important part. The top, not so much. This is very important, and we will use that a lot. This is the derivative of an exponential in terms of e to the x. This is the derivative of the exponential in terms of e to the x. So the derivative of e to the x is e to the x. Really? Yeah. E to the x is a very unique type of derivative. It's an extremely unique type of derivative. The derivative of e to the x is e to the x. You'll find a little bit later on, when we start talking about natural logs, it's the same thing for natural logs as well. The derivative of a natural log is very unique. It's very unique. All right. So let's calculate it a little bit. Let's use it. If f of x is equal to e to the x minus x, find f prime and then f double prime. And we're just going to calculate it. We're not going to graph it. We're going to find f prime and f double prime. Okay, so let's find f prime of x. Well, it was e to the x minus x. Oh, there's my difference rule. I've got a subtraction in there. So what can I do? I can just take the derivative of those two pieces and find them separately. Well, we just talked about it. What is the derivative of e to the x? e to the x. What is the derivative of x? 1. In this case, minus 1. So there's f prime of x. Well, what is f double prime of x then? Okay, what's the derivative of e to the x? E to the x. What's the derivative of the minus 1? It goes bye-bye, right? It goes to 0. So here's f prime of x. Here's f double prime of x. What's f triple prime of x? What's f quadruple prime? E to the x, and that can go on forever and ever and ever. Okay, the derivative of e to the x is always going to be e to the x itself. Do one more problem here. At what point on the curve y is equal to e to the x is the tangent line parallel to y is equal to 2x? Okay, now we're starting to get real fancy. Now we're not only examining what the derivative is going to be equal to, now we're saying, okay, when is the derivative going to be parallel to something? Okay. Now, thinking about this graphically, here's e to the x, right? And I want to know when that function is parallel to 2 to the x, or sorry, just 2x. So running through 0, 0, up to, what's 2.718 over 1. Here is the line that I'm looking for. Okay. At some point, the slope has to be parallel to that line. I'm not asking about the intersection point. A lot of common mistake is to just find the intersection point. I'm not asking when they're equivalent. I'm asking when is the slope equivalent to 2x. Okay? All right. What's the slope of that line? What's the slope of that line? Just 2, right? The slope is 2. Okay, I want to know when e to the x has the equivalent slope of 2. Okay. So let's find y prime. Because y prime is going to give us the equation of the slope. Well, what is y prime in this case? Just the same e to the x. Right? Just the same e to the x. So I know the equation of the slope is e to the x. And I want to find, the goal of this problem is to find when the slope is equivalent to 2. So guys, all I'm really going to do is just take e to the x and set it equal to 2. Now, how do I solve for x? Anybody remember? How do I solve for x? What do I take? How do I get something out of an exponent? The natural log. Log base e. Log base e of 2 is x. And remember, log base e, that's why I called it natural log. ln of 2 is x. Okay, let's just figure out the decimal real quick. ln of 2. ln of 2 is a perfectly fine answer. Or 0.69. Okay, but it didn't ask me for just the x value. I wanted what point on the curve. Okay, so this is really just our x value. I need to figure out it's ln of 2 comma something, or 0.69. I'm going to give it to you in both exact and decimal. Okay, let's plug it in. My initial equation was y is equal to 2x. Or sorry, excuse me, that was my parallel. E to the x, e to the x. And so I'm going to find y is equal to e to the ln of 2. Okay, now this is one of those unique properties of e and natural log. Remember, e to the ln is going to cancel. So that's just going to end up getting 2. Remember, if you have a log base and an exponent base of the same thing, they will cancel themselves. So ln of 2 comma 2 or 0.69 comma 2. Either way you want to give it to them. Okay. Any questions on that? So I think you're going to start to see a rhythm for the home or for the notes. We're going to start to examine things using our old definition of a derivative and saying, okay, what patterns do we see? And we're going to start to just learn the formulas, learn the rules for all of our derivatives. Like today this lesson we talked about polynomials and exponentials. The next lesson, let me look at what we got next. Let me go back to last year's 2021, just so you can see what's ahead. Come on, buddy. Calculus, chapter 3. We talk about product and quotient rules. What happens when we multiply two functions together, divide those two functions. And then section 3.3 is all derivative of trig functions. And then we get into this thing called the chain rule. Then we start talking about implicit differentiation. And then we do derivatives of logarithms. Okay, so we're talking all about different types of derivatives and how to solve different types of derivatives. Hyperbolic function derivatives. Ooh, those are fun. Okay, sorry, I'm getting a little foreshadowing there, but I'll shut up. All right, let me give you guys your homework. You can get started on it. You got about